So first off, let me start by thanking you for showing up. This time slot is packed. So I know that you probably have your coworkers at different talks, and there's probably no room in Dino's. So thank you for making this choice. You won't be disappointed, but we do appreciate it. Also want to take a second to thank Black Hat for giving Metasploit this track, and Val for putting this all together, because he and HD were the coordinators for a whole mess of people who are very uncoordinated. So that made for a lot of fun. So the talk today, okay, stay back here. The talk today is called Metasploit Autopsy Reconstructing the Scene of the Crime. Dramatic, I know. My name is Peter Silberman. I'm an engineer and researcher at Mandiant. I do a lot of malware analysis and development for the agent product.
And I'm Steve Davis. I'm a consultant with Mandiant. Primarily, I stick to the proactive side of the house, or pen testing. Also, I'm on the malware analysis team, and I do some exploit dev and research in my free time.
So that's who we are. This talk is a little unique, and you can tell by the agenda. Rarely do you see a half of a demo, and rarely do you see it at the beginning. So we're going to do both those things, actually. So we're going to do half of a demo at the beginning, sort of like a trap to keep you here, because you're going to be like, well, what's going to happen next? But there's actually a purpose to it. So we're going to do half of a demo. Steve is going to actually walk you through the demo, the first half. It's going to be popping it like it's hot. Then we're going to talk about the problem and the solution and sort of the goal that we're trying to come up with this talk. This is actually, if you haven't read the abstract or something, this is a defensive talk on the Metasploit track, and you'll sort of see where we're going with this talk. After we do that, we're going to do process acquisition, which is something some of you may be familiar with from the malware analysis world. We're going to talk about how it's currently being done by Ali Debug, Immunity Debug, WinDebug, and then we're sort of going to flip the script and show you how we do it at Mandiant and how and why we think the way we do it is plain and simple a little better. And I'll back that up. I will, I promise. We're going to talk about Metasploit. Obviously, you're not here to learn how to use it. We're going to talk about specific aspects of Metasploit that you probably are not familiar with. We're going to focus on Meterpreter communication from Metasploit console to server. So basically what's going on when you send a command, because how many people think about that on a daily basis? You just like that it works, because we all do. I mean, that's why we're using it. And we're sort of going to wrap up the talk with the release, which is now downloadable from our website, freely available, open source. We'll talk about it. It's a proof of concept tool called Metasploit Forensic Framework. And with the second half of the demo will be us actually utilizing that tool to reconstruct it like it's hot. So that's sort of how this talk is going to go. But before we go forward into the first half of the demo, you're going to notice that the slides on the CD don't match at all what you're going to see up here. And that's unfortunately or fortunately due to the fact that HD decided in his copious amounts of free time that he has now that he was on maternity leave or paternity leave for a little while, he would continually update the Metasploit project. So every day we'd wake up after we finished our slides and there'd be a new feature that we'd have to account for. So between the time that we submitted our slides and finalized our tool, HD added SSL support to Meterpreter and changed how it's loaded. And we'll discuss how that affects us or actually doesn't affect us, but these are all things that we had to account for in our slides. So that's sort of why things got shifted and changed, and so keep that in mind, because there were, in a 10-day period, 24 commits to SVN just by HD. That doesn't account for kernel ownage and things like that. So the project went under a huge facelift. So now I'm going to hand it over to Davis while he does the actual demo.
All right, so you guys can see we're running PowerPoint right now. You guys can't see that I have a Mac up here. So we have a virtual machine running a fresh install of XPSP3. And what we're going to basically do now is go back to our Metasploit in OS X and exploit this machine. So we're actually going to exploit the presentation machine we're using, or the virtual machine we're using to present, and then we're going to go back and later reconstruct exactly what I did or the attacker did right now. So.
And real quick, this is host only, so don't go looking for it.
We
are in the Metasploit track. This is a host only VM, so good luck. And we're not online, so.
All right, so we're using MS08067. I already have everything set up. I'm just simply going to run the exploit. All right, and we popped our virtual machine that's running our presentations. So just for this demo, we're pretty much going to do a few little things that an attacker would like to do in a given situation. We're going to basically focus on an attacker trying to dump some form of hashes in order to crack them using a rainbow table or what have you. So first thing we're going to do is just execute command shell. All right, and I'm just going to simply do netstop to prove, or netstop themes to prove that I'm actually running this on my machine. So you can see themes went away. Also, I'm going to do net users. And we see some interesting stuff. I like those users. Let's actually dump the hashes. All right. Also, I just want to get an idea of what processes are on the machine. So I'm going to dump processes. And finally, we're going to do a get PID. And you'll see why that's important later when we go back to our process acquisition and things of that sort. So I'm going to disconnect from the Meterpreter session. And when I say session, I mean basically what I connected to the machine, exploited it, ran some commands, and now I'm disconnected. So the attacker is gone and off the machine now.
Also, real quick, one thing I didn't say is we only do live demos that have the potential to crash. So you go to NASCAR for the potential car crashes. You're coming here to see if this is actually going to go the way we planned. It has in the past, but we're aware it might not, and it gives you guys something to look forward to. So I didn't say it before, but this is not a video. We were not going to do a video. We're going to do this live and see what happens.
Yeah, let's get out the Bud Light. All right. So as you guys can see, just to recap, we exploited the VM that we're running our slides off of, MS08067, nothing big here. So we have a problem now. A Meterpreter traditionally can reside completely in memory if the attacker chooses to do so. Now, if he wanted to do something like upload more malware to do further attacks, it's going to be a little bit more noisy and actually on disk. So if we were to acquire this machine right now using traditional disk forensics, like if we were to use DD, dump all the partitions, and then look at that through Encase or something, we wouldn't see any residence of Meterpreter being on the machine. So there's no real way to determine what actually happened and what we should be looking for as forensic investigators. So the goal is basically to reconstruct what I just did, the Meterpreter session, with as much reliability as possible. And the solution to that is basically acquire the exploited process's address space. And what we can do is parse out the Meterpreter protocol from acquired memory sections. So we're going to get into that in a little bit. Peter's going to give you a nice segue into memory acquisition and memory forensics. But what we're going to actually do is reconstruct that entire session that happened in memory. And we're going to use that by collecting these things called virtual address descriptors, which Peter's going to elaborate on in just a minute. While he figures out how to turn on his mic.
Yeah, you got to turn on my mic to talk. So before we go into the virtual address descriptors and sort of give you guys a crash course in finding processes in memory, acquiring the process in memory, and then how those packets look in memory, we first need to understand one aspect, and that's a tool. It's freely available. It's called Memorize. It stands for Memory Analyze. So you put the two together, and cutely enough, it comes out to Memorize. So, yep, we came without our own. No marketing department for that one. Yeah. So Memorize has the ability to do a couple things. It can enumerate all the running processes on the system. And when we're talking here, we're not making API calls. So it's actually accessing physical memory or going through a DD and enumerating all the processes on a system. It's then going to enumerate the handles that are open for each process. It's going to enumerate the memory sections that are utilized for each process. It's going to enumerate the ports that are open for each process. And it's going to enumerate the strings per process. So this is all done without API calls, and we'll sort of discuss how some of this is done. And we teach a class on this, but if you have questions that are sort of outside the scope, you can come up after, and I can explain some of this to you. Memorize also can enumerate drivers from memory. So all loaded drivers, you can get a list of that. That's helpful. Do rudimentary rootkit detection, which is nice. It also has the ability to do acquisition. So within this tool, you can do acquisition for later analysis. So we can take a full memory DD, if you'd like, from physical memory, dump it to disk. Or more importantly, and this is where our talk sort of pivots around, is Memorize can acquire a process's running address space. So the binaries, the loaded DLLs, the stacks, the heaps, the data, injected threads, injected DLLs. We see where we're going with this. So we'll expand on that, but we can acquire just the process. And we can also pull drivers out of memory, especially if they're hooking to hide themselves on the file system. You don't want to have to just unhook it. You can just suck it out of memory. Memorize works on both a live image, or both a live system, which you'll actually see today. We're going to demo on a live system because, again, live is more dangerous, a lot more fun to watch someone mess up on. But it also runs on an image. If we're on a live system, we're going to use the paging file. So we're going to get a lot more information because when pages are put to disk, we can actually pull them back out. We support a plethora of platforms and are moving to 64-bit, and 64-bit will also be free. So you're just getting what we make. So, and you can download it at our website. So that's that. let's talk about process acquisition. So where did process acquisition come from originally? How many people, just out of curiosity, raise your hand if you're familiar with process acquisition in some rudimentary form? So some of us are. All right. It was really sort of designed originally, I'm dated, I'm only 23, so it may have a further backdate, but from what I understand and what my belief is, it was designed for malware analysis. You had back in the day, back in the UPX Packer days, ASPAC Packer days, FSG, when those were it, and we didn't have the technology we have now, you still had to unpack these pieces of malware. So you'd run the piece of malware in some setting, either on a box that you could revert to, something like that. You'd acquire that process after it's run, so it's unpacked itself. You've got these Packer stubs unpacked, it's expanded, and then you'd stick that unpacked binary, or that one executable you acquired, into IDA, and that's where you'd go. That's sort of what process acquisition was and why it was utilized. Traditionally, it was done with debuggers. You'd have Ollie debug was really the first one I used with Ollie dump. It's a throwback, right? And back then, you'd find that it worked. That the pieces of malware, for most part, the general pieces of malware, weren't really debug aware, or they could be tricked into being acquired. You could set the debug flag to 0, things like that. But as we're going to show you today, acquisition has other uses, and some pretty cool uses. One example we talk about in class a lot is if you have a memory image and you need to determine what kind of malware is on that memory image, and you have no way to get that process or that malware out of the memory image easily. Well, you can acquire that process, take that executable, and submit it to VirusTotal. It's not a bad idea, and it works a lot. Another thing you'll find is if you're acquiring a process out of a memory image, your virus scanner will trip up when you're writing it to disk because it looks so much like what it was on disk previously. And sort of getting back to our talk here, you can acquire memory because we're going to acquire the full process address space, so you can get things like strings that were decrypted, right? So let's say you have a piece of malware. It's fully encrypted its strings. It decrypts the strings in memory. It makes some API calls with these decrypted strings. It then frees those strings, right? You have two ways that you can find those strings in memory. One is when you make an API call with a string, Microsoft has a tendency to copy that string into the heap somewhere else. So the piece of malware loses control of that undecrypted string. And the second thing is, and this is where we'll talk further down the line, is memory that's freed is still in memory and not scrubbed. That's key. Freed memory still resides there. So the strings that were freed are still there with the 4 bytes missing. And that's very helpful, and that's sort of where we're going to go with this. So classic process acquisition works the following way. You're going to open a handle to a process or attach to a process. Once you do that, you get a handle back. You make the API call read process memory right there. That's an actual API call. It's commonly what's used. It's going to read a virtual start address to a virtual size into a buffer, and then commonly what happens is that's written to disk. But let's talk about the drawbacks. And some of these you may be able to think of right off the bat. Some of them you may be new to you. It requires touching the process. And by touching the process, we mean you're making an API call to a process. So you're opening that process or you're attaching to that process. And if your malware is smart, it's going to hook those calls in some fashion and prevent that from happening. Zone alarm is an actual firewall. It hooks an open process to prevent that from happening. So malware can't actually get a handle to it. So that's a huge drawback. Touching a process is a drawback and is unacceptable in process acquisition, period. Second is debugging. If you attach to debug, debugger detection is trivial. OpenRCE has a library on anti-debugging methods. It's got, I think, 40 maybe different examples. It's all open source. Each one of those will break a different debugger or the same debugger over and over again. So using a debugger to acquire a process is also unacceptable. And finally, you're getting an incomplete picture of memory with current process acquisition. You're only getting that executable that's running. But what if you want that injected memory section or that injected thread or that injected DLL that's only in memory? How do you get that with current methods? You have a real problem. There is a way with WinDebug, but then you're debugging, so it sort of goes back to debugger detection is trivial. So that's what classes process acquisition and the drawbacks are. So memorized process acquisition works relies on the following. Memorize has its own virtual to physical address translation engine. So it works like the CPU. It'll take a virtual address, do the translation, figure out the flags, read the physical memory, and utilize that. It does not rely on attaching to a process. It doesn't open a handle to a process. It makes only inconsequential API calls. So we're not making things that are easily hooked. And we're not really relying on the virtual memory manager in the sense that we need them to do the translation for the memory that we're interested in. So to do process acquisition the right way, or the way that we do it, which may not be the right way in a couple years or when someone gets a hold of the tool and plays with it more, is we first have to access physical memory or give an image. Either one will work. Next, we have to find all the processes running on the system in physical memory. And finally, we have to parse those processes running on the system. We have to parse out their address space, the memory sections that process is using. So the first requirement was documented a while ago. I don't know how many have read the article by Crazy Lord in Frack, who talked about a while ago using device physical memory. Real quick, we're going to access physical memory for two reasons, either for live analysis or acquisition. And to get physical memory, as I alluded to just a couple seconds ago, Windows gives us a section object. That section object is called \device\physical memory. If you open that section object, you now can read physical memory. And you can do that in userland from 2000 to 2003 Service Pack 0. Service Pack 1 and up, you have to be in ring 0. So in that case, you have to load a driver to open the handle and then pass the handle back to userland. So when we come across a virtual address that we want to read in a process address space or in kernel, we're going to translate that to the physical address and read the physical memory. So that's how we're going to utilize physical memory. This is a diagram that's in our class. I'm going to go like a minute on it. Again, if you don't get it, it's okay. This is a little much, but basically what you have here is a process has a directory table base, which is a pointer to the page directory pointer table. This is PAE. We're not going to talk about non-PAE. That's a waste of our time. You have a pointer to the page directory table. The first two bits of the virtual address are an index into the page directory pointer table. That index is going to give us the page directory table base. The next 9 bits are an index into the page directory table base. That's going to give us the base of our page table entries. The next 9 is the index into the page table, and that's going to give us our offset into physical memory. And the last 12 bits are used to address physical memory page. And again, this was just put in, but if you don't understand, it's not going to affect the rest of the talk. But that's sort of how Memorize works on a high-level view. It does all of this, checks flags, determines if things are paged out, and it does it all inside itself. So once we've taken the virtual address, we've mapped it to a physical address. We've read that physical the data at that physical address into some buffer, 496 bytes into a buffer. We're going to do one of two things. If we're in acquisition mode, we're going to write that buffer to disk and just read another, and just continually linearly looping through memory addresses because we're writing it to disk. If we're in analysis mode, where we're finding something like live analysis, we're going to map that buffer, the physical memory into a buffer, and then we're going to scan that buffer because we're essentially scanning memory for something that looks like, in this case, an E process, for example. So we're looking for an E process in this buffer. Now, what are we going to do next? Well, I said the next requirement is process detection. So we have this buffer that we've gotten from physical memory, and we need to find the processes. All the processes that run on your system are represented by something called an executive process structure, or E process. So every process running has to have a corresponding process. It's just a matter of life. The process manager otherwise won't know about the process, and the process won't get scheduled. So you won't have it running. So within this structure, there are certain values that don't change per service pack. And if we scan the buffer for these values, we can identify the start of the E process structure. Now we're going to do some more checks, but we can identify these processes using this method. There are some caveats. An E process structure can exist for processes that have been exited. And that's of no value to us currently. We believe we do incident response, so it's ongoing. And you're also going to find that what we look for, or these D words that represent eProcess structures, exist throughout uninitialized memory. So you have to weed out the false positives, essentially, and that's a caveat. And I spoke a couple years ago about an effective way to do this. But there are a number of papers. It's very trivial, but it's also sort of outside the scope of this talk to get in depth about process detection. So we find the processes in physical memory. What next? So after we found the process in physical memory, we go back and say, well, the users told us what process they want to acquire. They have a suspicion that something's gone wrong with SVC host, right? It's commonly a process that's owned. So they say, find and dump SVC host's memory. So we find SVC host's eProcess structure. Within the eProcess structure is a member variable called VAD root. And VAD is an acronym. It stands for Virtual Address Descriptor. So it's Virtual Address Descriptor root. And this is actually a pointer to the top of a binary tree. It's a self-balancing binary tree. There's nothing special about this binary tree. Think back to Computer Science 102, whatever class it was where you did binary trees. It looks like that, left, right, child, parent, pointer. The entries in this binary tree are of MMVAD type. So it's actually Memory Manager Virtual Address Descriptor structures. That's what they're called. So the tree is made up of these MMVAD entries. These MMVAD entries contain information that's pertinent to the process and tells the operating system what memory it's currently consuming, essentially. So within these entries, there's a virtual start, which is the virtual start of the memory section it's describing. There's a virtual size, which added to the virtual start will give you the virtual end of the memory section that's being described. There are some flags and things that we were not going to really get into. But also within this MMVAD entry is a pointer. So if this MMVAD entry is describing memory that contains a mapped DLL or mapped executable. So the MMVAD is actually representing kernel 32 DLL's memory, or not memory, the loaded binary itself, like where the binary has been loaded. So this entry is describing where this executable or DLL has been loaded. The entry will actually contain the path of where that DLL came from, or where that executable came from. So you can say this memory section actually is kernel 32 DLL, or svchost.exe. And this structure is used by Windows to manage the process address space. And we're going to show you a diagram that hopefully makes this a lot easier to grasp. So real quick, this is the actual structure dumped out in WinDebug. Starting VPN is actually the starting virtual address. Ending VPN is actually the ending is the size. When you add the two together, you get the actual virtual end. Parent is the parent pointer in the binary tree. Left and right child are what they actually just say they are. The control area will contain a pointer to the path if the memory is describing a mapped DLL or a mapped executable. So real quick, I sort of think this is the easiest way to understand VADs. So OllyDebug has a feature called Memory Map. If you just hit Alt-M when you're attached to a process, it shows you the memory layout for that process. Each line is a virtual address descriptor, an entry in the tree. That's how you can think about it. So within this tree is all of the processes heaps, all of the processes stacks, all of the loaded DLLs, all of the executables. Anything that process is doing with memory is in this tree. And that's sort of by enumerating this tree, we can sort of enumerate everything the process is doing. And you can see also, if you note, it goes 10,000 hex, 20,000 hex, 30,000 hex, then 7B000. That space in between, Windows needs to know about, because if this process makes an allocation or starts a bunch of threads, that space may get filled in very quickly. So it's utilized by Windows to manage where it can allocate certain things. So that's the purpose of the virtual address descriptor tree. And for our uses, we're going to be using it to enumerate the process address space and get access to the heap, essentially. So here's a cool little animation. I think it's cool, at least. We'll see. The kernel address space are represented by these addresses right here. They contain data. That data you see right there. And remember I said we're going to map a page at a time, and we're going to scan for some characteristics of the eProcess. This D word actually indicates the dispatch header on XP, Source Pack 2 and 3 for that process. So we determine that this is a process, right? We cast it as such, and we parse the structure. Some of the interesting things that you can pull out are, the image name, the virtual address root, which is actually what we want. You can get the handle table, things like that. So we get the virtual address descriptor out of this eProcess, and then we walk it like a tree. It's just a binary tree. It's in kernel, so it's a little more intimidating because if you dereference something wrong, well, your box goes down. But we've all seen that happen before, so really. Yeah, not your box. So we walk the tree. You can see left, right, point to left, right, children, parent points back. Good to go. For each virtual start and virtual end, we write it to disk. So we're just walking this tree and dumping it to disk. Each entry is its own file, right? So what we end up with is this. And this resolution is really bad. I do apologize. But you can sort of see you've got the DLLs that were mapped. These .vad files are all memory sections. All memory sections. And it just goes on. So process acquisition with memorize allows you to dump the full address space. It's going to overcome most binary packing. Please don't raise your hand if you're a government employee and said, I've seen something, it's going to break it, you're going to die. There are always caveats. There always are. Most binary packing, it overcomes. Themida, when acquired with memorize and then bindiff using Dynamics, will have an 80% match with 99% confidence. So that's the kind of stuff you get when you deal with packed binaries unpacked in memory. It's not bad. We capture communication protocol strings through the heap, things like that. We're just dumping what's in memory, so if it's there, it's going to get written to disk. We're bypassing anti-debugging techniques, and that's sort of not rocket science because, well, we're not debugging, so obviously we're bypassing these techniques. And we're able to acquire things. We're able to acquire things like, I don't know, DLLs that are only in memory because, well, they have a VAD. Or code that corresponds to exploits that were on the stack, heap, things like that. We can pull that all out. And now it's Davis's turn.
All right, so you guys may be wondering, when are they going to talk about Metasploit? And we're going to get into that right now. So, I know you guys are all like, what the heck is Peter talking about? So I'm just going to give you guys, I'm sure a lot of you are familiar with Metasploit, open source exploit framework, originally developed in Perl by HD. Currently we're in, the public is Ruby 3.3 dev. It's platform independent. It has an array of payloads, but particularly for this talk, we're just going to stick with Meterpreter. So I'm just going to give you a background of Meterpreter and then kind of dive into Meterpreter and what's under the hood there. So Meterpreter is a next generation post-exploitation payload. So what that means is, typically if I'm an attacker, I want to get on a box. One way I want to get some way to interact with that box is send back a shell, whether that's going to be like binsh, cmd.exe. However, I'm limited to handles here of standard in, standard error, standard out, so I can not really do anything interactive. So let's say I wanted to upload more malware and I didn't want to spend the time of doing TFTP and create a batch file to do all that, or TFTP may be disabled. So what we can do is use Meterpreter to overcome a lot of these constraints. So Meterpreter is a fully functioning client-server interpreter, hence the name, and it allows us to do extensions for file upload and download. It allows us to do key logging, and recently we have network sniffing now, which is another great extension. So, and as I said before when I was speaking, it can be completely memory resident. So if an attacker chooses to, he can be extremely stealthy. And one other thing we'll talk about is Meterpreter comes with a lot of these default scripts. And what they can do is really automate an attacker's time when he's on a machine, and it can just be good to go. So it can be used completely to automate anything that we want to do in a given scenario, such as like enabling terminal services on a box, or disabling some antiviruses or what have you, or heaps, what have you. And a lot of these are included in the default Metasploit trunk, so they're good to go right out of the bat. Everybody has access to them. So we're going to get into Meterpreters basically under the hood right now. And I'm going to talk about the old default way and the new way. We had to, up until, I guess, last week, we were changing slides and changing our code because everything changed so much.
That sniffer module didn't come out till last week, for example.
Yeah,
so that's, sort of what we've been updating.
Yeah, we wake up and we see HD post something on Twitter and be like, oh, damn it. So then we'd have to like just go and change all of our stuff. So we're going to talk about the old way of injection. So DLL is going to get injected into an exploited process. It's going to be a staged payload, which is basically going to just open up a receive call on the machine and then write data sent from the attacking machine somewhere into heap. So the way that it got this library loaded, because remember, we're going to be, our shellcode buffer is going to be in heap somewhere. What it's going to do is hook lower level APIs, and I have those listed at the bottom there. I'm not going to really go through them all, but they're there for your amusement. And what this allows us to do is basically call load library without having to worry about the DLL being on disk or on some form of Samba share. So traditionally, if I was going to load a DLL or do some type of DLL injection, I'd have to have the DLL present on the disk. So if you're familiar with malware, malware usually likes to do this, and it'll dump a DLL on the system and then inject that somewhere, then kill off the injector binary. So that's all done. The metserv.dll is then running completely from memory, and we're good to go. I'll get into some issues, though, with the old way versus the new way in just a minute, but now I'll talk about the new way. That old way was originally developed by Scape and JT. The new way, which is reflective DLL injection, developed by Stephen Fewer. So what happens now in the reflective? The host operating system is completely unaware that anything just happened to it. So what's going to happen is there's going to be the same process. We have stage payload. We're then going to inject a DLL, but there's this really, really cool aspect of a shellcode bootloader stub at the beginning of the PE, and it's basically going to walk down the PE and set up everything it needs to then call this offset for a reflective DLL loader, which is a mini PE loader. So we're not actually using the Windows PE loader, we're using this custom one. So what that allows us to do is basically not have any handles in the process environment block to metserv.dll, and this is excellent. This is way more stealthy than before. So when the old method, we were able to see handles to metserv.dll. So if we opened up like sysinternals, process explorer, we would actually see metserv.dll sticking right out in front of our faces. The new reflective way, not going to be the case because the process doesn't even know anything happened to it, which is pretty sweet. And I just included the offset here from the PEB in memory order module list. That's going to be the offset at which we can see all the loaded DLLs. And pretty much it for that section. So now let's get into the networking aspect. We talked about how Meterpreter gets on the machine and what it does to get loaded. Let's talk about networking. So originally the packets were going to be in clear text over the wire, but now we have the awesome aspect of adding SSL. So that was another change that we had to go through. Fortunately, though, it really didn't do anything. All the packet structures are going to remain the same because in memory, which I'll get into in just a minute, everything's going to be in clear text. So getting to the Meterpreter packet communication. It uses this packet structure called a TLV, but in actuality, Meterpreter uses a length type value as opposed to a type length value, which is TLV. I'm going to refer to it as TLV from here on out. Just keep in mind that in actuality, it's LTV. So what this is going to do is provide a really nice and tight communication protocol for the Meterpreter server and the client. So between the attacker machine, the attacker box that's running the Meterpreter client, and then the victim that's running the actual Meterpreter server. Some things to keep in mind: 32 bits for the length and type fields, and then we can have n number of bits for value fields. So we can have also nested TLVs within TLVs, which is going to allow a nice little structure that we can then further out parse, which you'll see later in the talk, which is how our tool works. So I'm just going to go through a simple demonstration of how the Meterpreter communication works and the packet structure. So attacker's going to send the exploit. Payload's going to be just like we did before, a bind TCP. It's going to use the new reflective DLL method, which really doesn't matter in terms of what we're looking for. And then as soon as the attacker gets back the Meterpreter shell, he's going to want to do something. So in this specific example, we just chose get PID. And what that's going to do is basically send a get PID request to the Meterpreter server from the attacker, and it's going to have this TLV packet. And the specific packet that we have listed here is going to be packet type request, which means that the attacker is requesting something from Meterpreter. And you can see we have the type length value laid out here. The type's the packet type request. Length is going to be the size of the TLV packet. And value is going to be this standard API sys process get PID. Now this value is incredibly important to us because what happens here is this standard API sys process get PID, once it's sent and received by Meterpreter, Meterpreter has this nice little function dispatch table where when it gets that process get PID request, it's like, okay, I now have to do something. So I'm going to look up in my dispatch table or my function offset table what I have to do and what's associated with that specific request. And as you can see, Meterpreter is going to do the internal lookup for what we just requested, standard API sys process get PID. Then what's going to happen is Meterpreter is going to build a response to send back to the attacker, because obviously the attacker wants to see what happens after he executed a specific command. It's going to build that response, put it on the heap, and then actually before it puts it on the heap, it's going to call the get current process ID, no big deal. Put that on the heap. It's then going to build a response, send it back to the attacker, and then free that. So just to reiterate, this is a very important slide. So after the response packet is sent, it's then going to be freed by Meterpreter. And I'm just going to go through the packet structure here because this is incredibly important for you guys to understand to see how we're actually doing this. So this is a type response. We were looking at before in depth the request. So here you're going to see the idea of nested TLVs. So we have a length, size of packet. It's going to be a packet TLV type plain response. And then within that value, we're going to have nested TLVs. So we have a length, the TLV type method. So that's going to basically send back to the attacker, what am I returning data for? What did you request? And that's going to be the standard API sys standard API sys process get PID. Then it's going to use this other type of TLV, which is going to be TLV type request ID, which is going to be used for communication channels between the Meterpreter server and client. Then it's going to actually have the juicy data. It's going to have the TLV type PID. So this is going to be the result in hexadecimal value of the PID that it's currently being run under. So if we exploited SVC host like we did before, we ran the get PID and it was under 1080. So that's going to basically be returned to us, and this is exactly how that happens. And finally, it's going to be a TLV type result, which is just going to be some type of, if there was some type of error or what have you, if there was a permissions issue. And this is going to be null because we didn't have any errors. Now, we can see all this put together, and this is an extremely nice packet structure for Meterpreter to use because it's small and it's very effective at what it's trying to do. But keep in mind, this was before. This is all before. So before they added the OpenSSL, packet TLV type plain response, we're all talking about this before because we didn't change this once the OpenSSL was added. So just keep in mind.
And that type would be packet TLV type encoded or encrypted. It just changed the type and nothing else would have changed.
Right. So just keep that in mind. So remember Pete was talking about we use memorize to acquire a specific process, and then we're going to have these VAD files. Well, for right here, we just have a diagram. We opened up a VAD file. And just like on the network, this is all resident in memory, and we can see that. We see the standard API sys process get PID. Now keep in mind, we're looking at a response packet, and Pete's going to get into some of the issues with response versus request packets and what our tool actually analyzes. There's some caveats there, but we'll get into that in a little bit. But we can see this is the response. So we can actually just look through memory and figure out exactly what happened here. So our first is going to be the TLV type method. One thing you want to note, though, the length, being that the packet was freed, we aren't able to get the length value here, which doesn't really affect us too much. Next, we're going to have that communication channel I just talked about, TLV type request ID. And also, there's our actual data, the TLV type PID, and it's going to have a value of 3EC hexadecimal. And then a result which was going to be null because there was no issue involved running the get PID. So you guys can see it's pretty simple structure, pretty simple to parse through if we had to. But there's this one other aspect. So if we deal with scripts, you may be asking yourself, well, if I have a script, it's going to do a bunch of different stuff. In actuality, it's just utilizing those same functions that we talked about, like get PID or process execute, reg set value, reg query. So even though we want to do something like, let's say, get GUI.RB, which is going to enable terminal services on a remote box, and then we can add a user and password to that so we can just simply log in, it's going to utilize those same functions that are exported from metserv.dll to build or do all of its malicious intent. So all we really need to monitor for is reg query value, reg set value, and then sys process execute. And we can see everything that specific script is doing. We don't need to worry about them doing any type of magic behind the scenes. And another example would be the kill AV script. So this is going to disable a lot of heaps and AVs. There's basically just a structure with a bunch of different processes that could be in memory. What this particular script does is it basically calls get processes, looks for all the processes on the machine, then has basically a blacklist that it's going to want to kill, like sab.exe, some of McAfee's products, and then kill those if it finds them. So nothing really magical going on here, and we're able to see all that using our tool. So just to recap, the Meterpreter communication, TLV is going to be sent to Meterpreter. That Meterpreter command is then going to call a method from its function dispatch table. It's going to build a response on the heap, send that response to the attacker, and then immediately free that packet.
All right, real quick. I'm certainly not Ben Hawks or John McDonald, and I'm blanking on the other guy who just gave the heap exploitation talk. But there are some caveats to the heap that we need just to quickly discuss. So when you free memory, it's not immediately reused, and that's basically dependent on your system. You know, how quickly, what's going on, essentially server. If the process we're in is SVC host and it's on a server and has a lot of RPC requests, or it's a domain controller, you may see memory being reclaimed much more quickly. But you have something called a zero-page thread, and basically it runs at a lower priority than user threads. So your system has to become idle for this thread to execute, and this thread will go through and scrub memory so that it can be returned to essentially reclaimed, because Windows will not allocate a process memory that's not been scrubbed for C2 compliance. That's the big thing that has to be cleaned out, so you don't have essentially encrypted keys going to a user when you make an alloc request. We've done tests where we've utilized the system for 4 hours and seen the Meterpreter session still in memory. We've also seen it where 30 minutes later it was gone. So it's heavily dependent, and this is just a quick note. We'll actually have a caveat slide where we go a little more in depth on this, but just a quick thought there.
All right, so detecting the presence of Meterpreter in memory is trivial. So current detection methods that we're going to utilize is we could examine VADs for MZ or PE headers that have no name. So all of the acquired memory that's going to have a specific name, like kernel32.dll, user32.dll, if we see a VAD with no name, but then we see a PE header, something's going to be injected there, and we're going to actually use PE file to actually scrape that out, and you'll see later in our demo how that all works. Also, we can detect high entropy of VADs. Now, mind you, this is going to result in some false positives, whether we have strings or some type of encoded in strings, what have you, in memory. But it's very effective for finding actual executable code in memory. And the encryption of the SSL traffic works great against IDSs, which makes Meterpreter more stealthy. But the packets have to be, have to be decrypted in memory at some point for Meterpreter to actually act on them. There's no way that it could have an encrypted packet unless it was built to in memory and then basically look up an encrypted function offset or what have you, something not humanly readable.
All right, now to the meat and potatoes of this talk. So we call this a proof of concept tool, and there are a number of reasons we call it a proof of concept tool. So please don't think of this as a product, basically. It's open source, it's Python. It's sort of funny, Metasploit's Ruby, we went with Python. It's BSD license if anyone cares. I don't really know what that means, but that's what I was told to do. It is going to work with memorized acquired files. So it doesn't work on its own. You have to acquire the process, which is why we stepped you through how process acquisition works. You need that process acquired to run this tool on. And we're going to walk through the steps very shortly. It's got a pluggable framework, so like when HD kept dropping features, we just had to write new plugins instead of rewriting the product each time, or the proof of concept tool. So that would allow us, hypothetically, if something were to come out today or something and we were so inclined, which we're definitely not, we could write a plugin for it to handle it. But we're not going to, so don't worry. That link is active as of this morning, so you feel free to download it right now if you're brave enough to use Black Hat Wireless, or you can wait and get it somewhere else. It'll be up. You can get the link. It's in other slides too. So let's just talk briefly how the tool works. I think we've sort of alluded to it basically. We look at VAD files, right? And we specifically examine the VAD file for different methods. So we essentially went through Meterpreter's command dispatch table and said, here are the methods they support. And so we scanned the VAD, or if you think of the VAD as the process memory, for these method strings. What we do is then we found essentially with that method string, we found the first part of that TLV, the response packet. And we do a check to make sure the TLV is response. Obviously, we're not going to just parse it. We want to know that we're looking at the right thing. We're going to then parse out that TLV, just like you saw with Steve, where we had the beautiful broken down nested TLV. That's all we're doing. Because that TLV is such a well-defined structure, and kudos to Metasploit for coming up or utilizing this protocol the way they did. It's so well-defined that we can write a tool to leverage that and reconstruct what was sent. So even nested TLVs, because we have the length, we know what's coming up next, we don't even have to really know what the value is, though we do so that we can make a pretty print statement. So we're going to parse out the response. TLV, essentially what was sent back to the attacker. Because really what's interesting is what was sent back. And a lot of times we find that what was sent, we'll also find what was sent, and they look the same, so we'll print them out as well. This will indicate to an analyst what was executed. So if you're running on a machine and you see, okay, you run the tool and you see a hash dump appear on your screen, and you do this on your domain controller, well, you have a serious problem, and you probably aren't going to sleep for the next 2 or 3 days, because they've just taken all your accounts. And you now know that because you have the tool to essentially reconstruct what happened. So that's sort of how the framework works. Here are the supported commands. Sniffer supports all the sniffer module commands. That was, again, as you can tell from the commands that are supported, we were working on it up until last week. Sniffer supported ps, cd, makedir, rmdir, working directory, getpid, hash dump. Injected DLL is the command we added. It's not supported by Meterpreter itself. It will identify the injected DLL. So it will actually tell you, here's metserv DLL, here's SCD API DLL, here's priv DLL, there's incognito, and now sniffer. So you can have a number of injected DLLs, and we'll give each. Do we do sniffer? Do we name sniffer?
I don't think so.
No. Okay, we don't name sniffer. That didn't make it in, but all the others we do name. We have a keylogger. We support all the key logging, so you can get back the keys that were put into memory from the buffer. So like if they were logging keys, you can see sort of sometimes what keys were logged. Kill, you can tell what processes were killed, and this will go back. We'll demonstrate sort of with the script how this works. LS, so you can see what file listings they were. So combining the CD and LS, you can sort of see where the attacker navigated on your file system. Migrate, if they pivoted into a process. For example, if I saw them migrate from SVC host to Explorer.exe, I'd assume they were going to start doing some keyloging potentially. That would make the most sense to me. Reg star is essentially all the registry commands, reg query, reg set, reg delete, all of them for key and value. Timestamp just wipes out the mace attributes. I don't really know if anyone actually uses that or understands that, the ability of that, but we put it in anyways. I think it's just there for you know, it was put in a while ago by Vinny. So interfaces, if they list off the interfaces and system info. So we really went through and supported almost every Meterpreter command. So here's our script versus MSFF, which we've decided to go with an acronym for. The Meterpreter API for this script, as Steve said, is reg query value, reg set value, and system process execute. If you wanted to see if this script will execute, you could execute the following 3 commands and determine what data was sent back. And you might be able to see, all right, they did run this script, or they just did something very similar.
We then deprecated basically single commands. We used to have it where it was just single commands, but now we added the dash all, which makes your life a lot easier. Yeah,
you can just do dash all to turn everything on. So that's what we're going to do for the demo. But we have the single command still in there because we didn't have the forethought originally to put the dash all in there. But
we have so many, like we'd forget what commands were, and we'd be like, oh, damn, we got to go back. And yeah, dash all is just the win.
So the other command like you can do for the kill AV is get process enum and get killed PID, and that'll sort of determine if you start seeing Process Explorer and some of your antivirus getting killed, you could sort of infer that this script was run. All right, caveats and gotchas. And then we're going to go into demos, so just hang tight, I promise. You'll get to see well, you may not get a car crash, but you get a cool race at least, right? So you gotta, so acquiring the exploited process does not always yield 100% results with Metasploit Forensic Framework. And I can't stress this enough. The demo we're doing is live. We've worked on it, we've tweaked it, we've got it in a VM. We can control a lot of the environment so that we can hopefully make it look like it works every time. But that's not the case at all. And we can't be more clear, and that's why we call this a proof of concept. It won't work every time. Our hope is, and what we believe, you will find parts of it. So, for example, if I run the dash all command and I see a migrate, and that's the only command I see, I know that the attacker didn't just migrate to Explorer.exe. They did something else. But that memory might have been reclaimed. So I might infer that, okay, the keys were logged, and I might go talk to the user and see what they were doing at the time that this attack occurred. So you need to extract, you need to put your investigator cap on when using this, because you're not going to get the full, in some cases you will, in some cases you won't. But we need to make that very, very clear. The other thing is, we originally said, we're only dealing with response packets, and that's not true. We also deal with sent, so what the attacker sent to Meterpreter. And the reason is, when an attacker in Meterpreter does a reg set key command, the string that the analyst is interested in is actually what's sent. Only thing Meterpreter sends back is actually a response code. So looking at the response TLV would yield the analyst nothing good. So The registry itself, the registry commands are very volatile because they're being sent and that memory seems to be being reclaimed more quickly for whatever reason. And I can't sit here and tell you X, Y, and Z is why. I have some theories, but they're definitely, just theories. So in this case, we're actually detecting the sent TLVs and the received TLVs. Whereas in other cases like process listing, it's just the sent TLVs. All right. So conclusion means we're getting close to the demo. I know, yes. The Windows Memory Manager gives analysts a chance to see artifact memory, and that's just going to be a fact of life. And that fact is very cool. We believe this has a pretty large impact for memory forensics, since there aren't too many people talking about memory forensics publicly, and that's also due to the fact that very few people are doing it. Would make sense, right? What do we think the impact for the Metasploit project is? I saw one article like hacking Metasploit, and our names were associated with it. It's not the case. HD will have an update on Sunday. Unfortunately for us, there'll be an update Sunday. We've spoken to him. It will, it will what we believe render the tool useless.
If you can't break his kneecaps, so he can't get to a computer. I'm just kidding.
It's the name of the game when you're doing a cat and mouse with offensive and defensive. We were very thrilled to get to speak today on this track in a defensive manner. We're going to get a kick out of showing you guys what we've come up with. If you're using previous versions of Meterpreter, backdated versions, obviously this tool is going to work. We will update the tool to detect the presence of Meterpreter, because he's also going to break us in that aspect on Sunday again. So we will update it to essentially detect it, but the reconstruction of the session is going to die on Sunday, we believe. For the dev, I don't know when he's going to put it into a tarball where people can actually apt-get it and things like that. So there may be years down where you're still able to use this tool. But if you're pulling from SVN, which is what we do for our stuff, he's going to put the fix in. So, that's the name of the game. We worked hard on it, and it is a pleasure to present this to you. Our hope is that by combining memory analysis and further research, we can take this to the next level and have more fun projects. Lord knows I have not given up on playing with Meterpreter, since it's a lot of fun, and who knows what we'll come up with next. But that's how it works. So we're going to go ahead and do the demo now, right? That's the next slide. Yep. You're going to get to see me use a Mac. I don't use Macs. I don't understand why you can't have two buttons. That just throws me off. So this is going to be fun.
It's elegant.
It's horrible, in my opinion. But so we'll just ignore that aspect. But I figure everyone's here anyways because they use Windows, and so everyone can be on the same page about this one button thing, but who knows. All right, so I have, there we go. I have Memorize installed in this VM. You can run Memorize from a USB key or a CD. So if you're actually doing real incident response, you can do that. This is what the install directory looks like. There's a bunch of batch scripts that allow you to control Memorize, because there we go already with the Magnus. That allow you to control Memorize without having to edit the XML. So the PID that was exploited was 1080. This is Memorize running. There's another component to Memorize, or essentially a GUI interface called Audit Viewer. It's available on the website. It's out of the scope of this talk, but if you don't like command line, which some people don't, like if you use the Metasploit GUI, you're going to want to look at Audit Viewer, versus if you don't, then you want to. I'm just saying, I use Audit Viewer and I use the console, so I don't know. You could do both. So real quick, we're running on live memory. It's an XP system. We determine this all dynamically from memory. Service Pack 3, no API calls. The results are going to get written to this audits directory here. It's created directory. Here's its scanning, actually. It's stopped here at SVC host because it actually found the process it's looking for. If we go into this directory, it's going to take a second because it's pounding the disk right now, writing files to disk. But, oh, lo and behold.
Like, damn, it worked a little bit.
Yeah. So this is the process address space of SVC host. The VADs are memory sections. It's, I believe, still writing. Let's see. Yep, yeah. Still going. And again, this is, imagine what this would be like on an enterprise system that's actually connected to the internet. You could get a lot more. But that's cool. Of course, so 1 second, please. 2 fingers, quick.
You had to do select all.
Yep. All right, so I'm going to just start up into the command prompt here. We go to desktop. This is here. This is what essentially what the package you download is. It's just MSFF.
And if you guys want to write modules, we have a module folder. You basically just follow our module structure, pop it in there, and then you can write your own. It's pretty simple.
So if we run it, you get the help. You can use one command. I don't know why you wouldn't just use the all, and I'm not sure why we didn't think of that, but we didn't. So we added the all last, as you can see, because it comes up last. So -- all. Look at that. And here's the moment of truth. It's going through the directory. Oh,
it worked.
So let's go through the results real quick. Like we knew it was going to work. It's just nice to see.
We knew that.
Yeah. We also, the cool thing is we've got the full session, so that's sometimes rare. So let's go through what the attacker did. Remember, he executed command. Here's where we're telling you the attacker executed command.exe. So you now know that the attacker popped a shell. Before that, we actually found the netserve DLL, and it's in this VAD right here. This is data that was sent to the attacker. So this is actually the command shell being sent back to the attacker's screen. Here's where the attacker set the net stop themes. Here's the response from the command shell. Net stop themes was successful. It should be noted that, one, you're not going to find these things linearly all the time, so you may find one command first. It doesn't indicate, it'll look like it worked in this case. Also, the get PID command is used in a bunch of different function commands, so you may see it propagated more than once, even if the attacker only did it once. So netstop themes, we've got standard API, priv. Here's where the net users was executed. We don't have the net users command, but you can see the result, so you can sort of infer what happened there. Hashes. That's fun. And this machine is going to be completely wiped. It's a QA machine and has no password, so don't bother copying this down. Here's where the process listing occurred. Yep, process listing. It's pretty cool. And then you get a summary of the results. So that's the tool working. Again, you're not guaranteed to have these results. We've seen it work really well. We've seen it work somewhat poorly. Usually you can get something, though, and that's the point you can take home. We did a remote attack. We have some time here, right? We got like 10 minutes. 10, how much? I'm looking. Oh, 20.
20, all right.
Look at this. So that was a remote attack. We're going to do a browser exploit now.
All right, so just as we did MS-08, we're going to do MS-09-02. So this is the awesome heap corruption. So let me open up my interwebs. And so let me go back to my Mac machine really quick. So I just have another Meterpreter or Metasploit session running here, which is running the, like I said, MS-09-02 memory corruption vulnerability. And let's go back in our machine. And I just helpfully put a link called Pwnage.
Which is usually how people get owned, actually, by clicking links called Pwnage. You come up with more creative things, right? Yeah. So Davis is doing this because we found by him not hitting enter on the screen, it will crash Internet Explorer and not actually. Yeah,
I don't know if it's for Ruby. I'm not a
so
big.
We're going to let talk to HE about it, but he is doing that for a reason.
Yeah, we're not big Ruby guys, and we were trying to not learn Ruby, but that didn't happen. So. Unfortunately. So it looks like we have a session established. I'm just going to connect to that session.
And one quick thing to drive home, that demo, which I totally failed to mention, we popped that box about 40 minutes ago, did a full presentation on that box, and then we're able to still get almost all the commands. So we did that. The point we were driving home is that this worked, and we were not scared to do it where we could have a time and utilize the system. So think about it. The box was popped. That's why we did the beginning of the presentation. You sat through the whole thing. Thank you. And we then reconstructed it. So that's sort of the point we're driving home. We're going to do this one very quickly and not have that time lapse.
Yeah, in my own personal testing, one time I exploited the box, disconnected, and left for work for 10 hours and came back. And then I was like, oh yeah, I was doing something. And then I went back and it was able to still acquire 100% of the Meterpreter session. And we've tried it both with creating scripts to just automatically connect to Samba shares over and over again, watch Flash, open up IE, close IE 100 times, and we've pretty much seen good results with it. But like we talked about before, we're not giving you the 100% golden ticket. You will absolutely find everything with this. So,
Hence
all right.
proof of concept. Yes, till Sunday. Again, till Sunday.
So we're going to execute a few commands here. Just going to do a process list. Now, mind you, too, we exploited IE. So I didn't specify a particular exit function. If I use like an exit function of thread instead of process, I could still keep IE. However, it would be unusable because of the exploited thread. As soon as I disconnect from Meterpreter, IE is going to go bye-bye. So what we have to do is basically a live acquisition. So as soon as the exploit's running and the Meterpreter session is established, we're going to also acquire the process. So another thing I'm going to do, change directory to C. I'm going to download boot.ini. All right. And
Do you want to kill a process?
yeah, we'll kill a process.
Kill command.
Yeah, let's kill cmd.exe. Yeah. All right, and we can just solve my command shell. If you guys saw in the background, that went bye-bye. All right. And now we're going to acquire. So I don't want to disconnect the Meterpreter session. I'm actually just going to go acquire. So
1584.
.1584 is going to be my process. So that's how, if you guys are doing like your own internal testing with our tool, recommend just running get pid at the end, just so you can figure out what process you need to acquire. You can acquire the entire process space, but it's a lot larger and a little bit slower, so we usually just home in on a particular process. So hopefully Pete kept me in, yeah, good. So I'm going to do process dd.bat. What was it,
1584, does anyone remember?
We've done this with so many different processes, I can't remember anymore. So just like we did before, we're going to run memorize and go through, and then we're going to run our MSFF tool.
Do you want to get the path? So we can get the question.
Yeah.
Or just, you can, yeah, open the directory up too. Oh, yeah, that'll work. Directory, yeah.
All right, so I'm going to wait for memorize to actually acquire the process.
Does, so this is going to put us right, it's going to mess with our time a little bit. Does anyone have a question they want to get with now? And then we can, yeah, shoot.
Has this framework been used in any litigation yet? Is that improving in the courtroom yet?
The question was, sorry.
Hell no.
The question was, has this framework been used in litigation or been proven in a courtroom yet? The answer, I'm sorry, is no, it has not. In fairness, we haven't, this is the first day we publicly released it. If you want to talk to me about that, I'd love to go to a courtroom and talk to someone about this, but I don't know. No, it's not. I don't know the legal ramifications of that actually occurring. Open source probably helps the case or hurts. I don't know, but no, it's not, and we've not. But you know, it's not saying never. Any other questions? All right, well, we're going to finish this up, and then we'll ask again if there are more questions, because well, maybe someone thought of something. So we're going to do the dash all again.
Am I frozen up?
Yeah, do dash all.
Yeah, no.
And then we'll see what we see. This is this may be an example of where we sort of went off script.
Nah, it's going to work great.
Don't know what's going to happen. It'll be fun.
I just jinxed myself. Oh, we're great.
Downloaded file, killed process ID. What else are we going to find? Anything?
She's still chugging. There we go. So we found our injected threads, or our injected DLLs. We found when I did a PS list. Do we got our kill?
Yeah, we have the kill.
Where's that at?
It's the top.
Top? Oh, yeah, there. Killed process ID 1392.
And we also handle upload files as well, so had the file been uploaded.
Yeah, so we do down up. So
and one other side note, because we acquire memory, you can actually, if that downloaded file is still in memory, you could actually pull it out of the process address space. So that would be neat. Questions again?
Are you using the acquisition for mostly improved interpreter, or are you
That's not a bad idea. I think someone's done it. Did you do a blog post on it? You can do memory acquisition. I'll look into it. You could upload memorize and actually do the acquisition and do it all remote. That'd be funny. Any other questions?
Thank you for coming.
Yeah, thanks for coming, guys.